Good day, everyone. Today I will be presenting section 1.2, 1.3, and 1.4 of our assignment, which focus on the following topics: postfix notation, stack diagram, and zero address machine instructions. Let's start with the postfix notation for expression. Z equal to P plus Q divided by M minus N plus R multiplied S minus with T divided by U. Firstly, convert P plus Q to PQ plus, and then convert M minus N to Mn minus. Divide the two results, that means PQ plus and Mn minus. Similarly, convert R multiply S to Rs multiply, and then convert T divided by U to Tu divide. Subtract Rs multiply minus Tu divide. Finally, add the two sections to form the complete postfix notation. Z equal to PQ plus Mn minus divide Rs multiply Tu divide minus plus. Moving on to the stack diagram, which illustrates the step-by-step execution of the expression using a stack structure. Here is how the stack involves: push P, then push Q. The stack now has P and Q. At the top two values, P plus Q, and replace them with P plus Q. Push M and N, the stack becomes P plus Q and M and then N. Subtract M minus N, that means P plus Q, M minus N. Divide P plus Q by M minus N. It will change to P plus Q divided by M minus N. Push R and S. The stack now has P plus Q divided by M minus N and R and S. Multiply R S, and that will become P plus Q divided by M minus N and R multiply S. Now push T and U. The stack becomes P plus Q divide M minus N and R multiply S and T and U. Now divide T and U. It becomes P plus Q divide M minus N and R multiply S and T multiply U. Subtract R multiply S minus T divide U. It will become P plus Q divided by M minus N and R multiply S minus T divided by U. Finally, add the two sections to get C. P plus Q divided by M minus N plus R multiply S minus T divided by U. This step-by-step process ensures that all operations follow the postfix order using the stack. Finally, let's look at the zero address machine instructions. In a zero address machine, operations are performed using stack-based system. For our expression, the instructions are: push P onto the stack, push Q onto the stack, add the top two values P plus Q, push M onto the stack, push N onto the stack, subtract M minus N. Divide the two equation it will become P plus Q divided by M minus N. And then push R onto the stack, push S into the stack, multiply, it will become R multiply S. Push T onto the stack, push U onto the stack, it will become divide. That means T divided by U. Subtract R multiply S by divide by U. Add the two results to get Z. The final pop Z command remove the result from the stack and store it in Z. This structure makes use of only the stack, adhering to the zero address architecture. To summarize, I have presented the postfix notation, the stack diagram, and the zero address machine instructions for the given expression. Each step demonstrate how operations are systematically handled in computer architecture. Thank you for your attention.
Good evening, Madam Julie. My name is Sidik Sarip bin Muhammad Nasir, and today I will explain how to translate the given mathematical expression into machine instruction for one address, two address, and three address architecture. The expression we are working with is basically here, like this. So I will walk through each type of machine instruction step by step, starting with one address instruction. In one address instruction, operation rely heavily on accumulator and intermediate result are stored in temporary variable. Here is how we can calculate the given expression. So first we calculate the left hand side, which means this part. So that we calculate first. So that we have to load P first and add Q into the bracket. So we first do the inside the bracket one, so that we load the P and add Q. Then store the result in a temporary variable, which means store R1. That is the temporary variable. So then we have to load M again and subtract with N and divide into R1. Divide R1 by the result and store it in R2. So that store in R2. And next for the right hand side, load R multiple with S and then store the result in R. So that store R3. So and then next we have to load T into the accumulator. So that load T divide by the U, and we have to subtract the result from R3, so that we have to sub R3. Finally, we want to combine both parts, add R2, add the first part to the second part, so that add R2, store into Z, store the final result in Z. This approach emphasizes the step-by-step use of accumulator and temporary storage. So that's all for the one address machine instruction. So that we have to, the next part is two address machine instruction. In two address machines instruction operate directly between register or memory location. Here is how we can compute the expression. For the first part, P plus Q and M sub with N. So that we have to move R1 and P. Move P to register R1. And then add R1 and Q, which means add Q to R1. Then move R2 and M, which means move M to register R2. Then sub R2 and N, subtract N from R2. Then divide R1, R2, which means divide R1 by R2. For the second part, R multiple S and subtract T divided by U is move R3 and R, which means move R to register R3, then multiple R3 and S, which means multiple R3 by S, and then move R4 to and T, which means move T to register R4, then divide R4 and U, divide R4 by U, then subtract R3 and R4, like subtract R from R3, R4 from R3. Then finally combine both parts, like add R1, R3, add the first part to the second part. Then move Z and R1, move the result to Z. This this is the method is more efficient since it reduces reliance on temporary storage. For the last is three address machines instruction. So the in three address machines operation can involve three operands, make it most efficient for the problem. Here are the steps. First, compute left hand side. Basically, we have to do this part. So that we have to add R1 PQ, which means 8, and sub R2 like M and N, then divide R3, R1, R2. Divide R1 by R2 and store the result in R3. Next, compute the right hand side. Multiple R4, R and S, divide R5 T U, which means divide T by U, store the result in R5. Then sub R6, R4, R5, subtract R5 from R4 and store the result in R6. Finally combine both parts. Then we have to add Z, R3, R6, which means add R3 and R6 and store the result in Z. The three address machine is the most efficient for complex calculation as it minimizes the number of intermediate steps. So basically this is my part. Thank you, Miss Julie. Thank you.